Hello, this is part 1 of a 3-part series of deriving the PID controller from scratch, purely from the math. A lot of videos I have seen jump straight into the definition of the parts of the PID controller without explaining where they come from and what role each part fills. In this video, we are going to start with the derivation of the P controller, or the proportional controller. First question every control system needs to answer is about the stability of the aerodynamics of the system. If the aerodynamics are not stable, then you cannot tune them. So our goal is to come up with a control law that makes sure that the aerodynamics are stable in our linear system. A linear system is defined as follows. In this video, we will work in discrete time, as it can be represented in simulation and code. We will also define our output as the state itself. This system defines the dynamics of our state. Our state can be a single value like speed, torque, or voltage, or a list of values in a vector. U defines the input of our system. This can also be anything defined by the system. The A value shows how the next state will evolve according to the previous state, and the B value shows how the next state will be affected by the input. In this video, we will deal with a single state and input, making A and B scalar values. All the math can be extended to matrices. Once we define our linear system, we can understand its behavior by separating it into 2 parts, the homogeneous response and the forced response. The homogeneous response describes how the system evolves from its initial state when no input or external influence is applied. It depends solely on the system dynamics and, if the system is stable, naturally decays to 0 over time. The forced response, on the other hand, is the part of the system's behavior caused by inputs or external factors, showing how the system reacts to commands. It initially starts at 0. Together, these 2 components fully describe the system's evolution, with the homogeneous response capturing the natural dynamics and the forced response capturing the effects of the inputs. Going back to our goal, if we treat the error as our state, then to ensure stability, we need the homogeneous response of the aerodynamics to decay to 0. This behavior is described by the following equation. When lambda is less than 1, the homogeneous error response naturally decreases over time, eventually approaching 0. The value of lambda determines the rate of decay and is referred to as the pole of the system. Once we deal with the homogeneous response, then we will be equipped to deal with the forced response, as the aerodynamics will be stable. If this is unclear or confusing, the math derivation example should help clear this up. So starting with our dynamics, our goal is to control the aerodynamics and make sure they are stable. We first need to define the aerodynamics. To do this, we will define the reference at time n as r of n equal to a constant, followed by the error at time n being the difference between our state and the reference. Now that we have the definition for the error of our system, we can bring back the homogeneous aerodynamics that we are trying to achieve. Let's first get the aerodynamics from our linear system. We start by subtracting the reference at time n+1 from both sides. We now can see that the left-hand side becomes the error at time n+1. Next, we subtract a times r of n from both sides. We see that those terms naturally combine into a times the error at time n. After moving terms around, we now have the aerodynamics of our system. Let's look at the 2 terms on the right. In most control systems, the reference at time n+1 really should not change that much from the reference at time n. When discretizing systems, dt will be very small. Therefore, the change in reference should be 2. Therefore, we can write those terms as one term equal to a-1 times r of n. We now have our final aerodynamics of our system. Let's find the homogeneous dynamics. To find the homogeneous dynamics, we set the input and the extra external term due to the reference to 0. Right now, the dynamics depend solely on A. If A is greater than 1, then our aerodynamics will be unstable as they will grow every step. So, we want to be able to control the stability with our input. To do this, we need for our input to be solely dependent on the error, so when looking at the homogeneous response, it doesn't disappear. We define u as minus k times the error at time n. We need to add in a parameter k so as to control how much of the input depends on the error. This will make more sense later. We define it as negative k due to convention. Now we rewrite the air dynamics with our newly defined input. Now combining like terms. Finally, we write our new homogeneous equation. As we can see now, our homogeneous air dynamics will be stable if the entire term a minus bk is less than 1. Now, if a is greater than 1, we can simply adjust our parameter k to make that term what we want. The pole of our homogeneous air system dynamics is equal to a minus bk. We want to be able to control the value of this pole and specify the decay rate we want. Solving for k yields the following solution. Now we can select a pole/decay rate, find k, set up our input accordingly, and our system's air dynamics will behave how we wanted it to. This input, u equals minus k times air, is exactly the p controller in a PID controller. We can now see precisely where it comes from and why it is so important. Now we will show what this does in practice with the real system. For our example, we will look at an RC circuit driving a load. An RC circuit has a resistor R, capacitor C, and our load is a resistor RL. We can imagine we are driving an incandescent light that is modeled by resistor RL. Let's say we want to control the light's brightness. The light's brightness is regulated by the voltage across it, which is the voltage across the capacitor, Vc. Vc will be our state that we will control with our input Vin. We define a reference voltage Vr that we want our capacitor voltage to follow. Our first step is to find a linear system that maps this problem. We start by analyzing the circuit using Kirchhoff's current law at the top node. This is not a video about circuit analysis, so if you do not understand how I got the definition of the system, it is okay, the control theory still applies. We solve the equation for the dVc dt term. As you can see right now, this equation is in continuous time. Therefore, we need to use an approximation to get it into discrete time. We use the backward Euler approximation. If our selected dt is small, this is an accurate approximation. We substitute this into the equation. And we rearrange the terms to solve for Vc at time n plus 1. Finally, from this equation, we can recognize A, B, and U. We now have our linear system that maps the problem. Now that we have our system, we can now use our P controller as our input to make the homogeneous air dynamics stable. Now that we have Vn, let's graph our system over time to see what our control law did. We show the reference voltage, the yellow dashed line, our Vc as a blue line, and Vn as a green line. Now let's see how these values evolve as our system starts from rest. So what happened? Why did our voltage not reach our reference? Well, remember, our control input did not guarantee this. All that it guaranteed was stable air dynamics, and that is true. The error between our voltage and reference did settle to a value, just not 0. Let's graph the air dynamics to see this happen. As we can see, the homogeneous part of the air response decays to 0, exactly as we designed. However, external forcing from the reference introduces a forced response, and the final value of the error is dictated by this term. This remaining value is called the steady-state error. We will now derive where this comes from. We will again start with our linear state space system and define our air dynamics. To keep the math smaller, let's replace A minus BK with lambda. And the extra forcing term, R times A minus 1 with D, stating that the reference is constant in this instance. Now let's write out a couple terms of the error to see how it progresses through time. Using the definition, we write down terms from E0 to E3. Let's take a look at E3 and combine terms. We can start to see a pattern. I encourage you to write it down yourself and see if you can find a closed form solution for E. Final solution takes this form. The homogeneous response of the error is the first term. As can be seen, the homogeneous response will go to 0 if lambda, the pole, is less than 1. Now, this is the forced response. We can see as n goes to infinity that this will take the form of an infinite sum, with initial value d and ratio lambda. The exponent on lambda counts backwards from n, but could be redefined as simply lambda to the n, in the case where n is infinity. Using this geometric sum, we can get a final value for the forced response, and this is called the steady-state error. As the homogeneous response decays to 0, the forced response remains at this value. This is exactly what we saw in the circuit example. We can rewrite our error dynamics in closed-form solution using the regular terms, and get the value of the steady-state error in terms of the system values. In this video, we derived the first part of controlling a system, which is making sure the homogeneous response of the error dynamics is stable and decays to 0. We found a control law to do this, and saw that it is the definition of a P controller. Next, to get rid of the steady-state error and have our total error dynamics go to 0, we will need another control law. In the next video I will cover this, which is the role of the integrator in a PID controller.